Hello, in this video we're going to take a look at infinite series that have some terms positive and some terms negative. We're going to encounter the ideas of absolute and conditional convergence and also work with what are called alternating series. So in previous sections we developed tests to determine whether a series converges or diverges. These include the integral test, comparison tests, the ratio and root tests. But these tests have one thing in common. They are all used to determine the behavior of series with positive terms. We've had one test so far that can work with series that have both positive and negative terms. That's the nth term test, and that's still a very important one to keep in mind. It's a good quick way to determine divergence of some series. If the terms of a series do not tend towards zero, then the infinite series diverges. So we're going to start looking then at series of this form. This one starts off 1 plus a third, but then minus a half, plus a fifth, plus a seventh, minus a quarter, etc. So this has terms, some are positive, some are negative, and because of this mixture of signs, we cannot use any of the tests mentioned above. Now, we have two options in a case like this, and the first, in fact, one we almost always do, is to investigate absolute convergence. And what this means is this. We simply look at the series of absolute values of the terms. So let's let summation bk be an infinite series of mixed terms. By mixed, I mean some positive, some negative. And if the infinite series summation k equals 1 to the absolute value of bk converges, it then turns out that the series with the absolute value signs removed also converges. And in this case, we would say that the infinite series summation bk is absolutely convergent. So when we say absolute convergence, we really have two series involved. We have the original series without absolute values and this series with absolute values. And if this series converges, so we test this one first, then we would know this one converges. That's our conclusion. So convergence of 1 implies convergence of 2. But then we would, in referring to this phenomena, say the summation k equals infinity of just the series bk is absolutely convergent. This is going to be one of our main tools for working with series of mixed sign terms. We first consider the series formed by taking the absolute values of the terms, and if this new series converges, then so does the original series with mixed terms. Be careful though, if the series formed by taking absolute values of the terms diverges, then we can conclude nothing about the original series with mixed terms, and more work is going to be needed in such cases. So again, many of these tests come with little warnings, and here's the warning for this absolute convergence idea. Let's look at a couple of examples. So let's see what we can say about either of these series, part A, part B, using the result we just quoted here about absolute convergence. So in each case, we'll take a look at the series of absolute values. Okay. These both have strange sign patterns. They go plus, plus, minus. And again, neither series then has strictly positive terms, so we cannot use any of the positive term convergence tests that we used earlier. At least we can't use them directly. Now, let's go to the series in part A. It has mixed signs, so we take the absolute values of all the terms, and that's what we see down here. And of course, the result then, with a little rearrangement, then gives us just 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc. Just kind of move these terms around a little to put them in. This last is a p series with p equal 2 bigger than 1, so we know that it converges. The series of absolute values of the terms of the series converges, and that means the original series is absolutely convergent. Okay. In part B, very similar, we take the absolute values, and once we do that, we see the harmonic series emerging. We know this series diverges. And unfortunately, if this series of absolute values diverges, then we can say nothing about the convergence or divergence of the original series. So as far as the behavior of this one, this is still up in the air. We could determine that this one converged in part A, because the series of absolute values converged, but there's nothing more we can do about the one in part B. Now, if the mixed term series does not converge absolutely, then our options are rather limited, but there is one theorem we will use now and then that actually shows up quite often, and that involves what we call an alternating series. So let's let A1, A2, A3, etc. be positive numbers, with A1 bigger than or equal to A2, bigger than or equal to A3. That is, these numbers form a decreasing sequence, and we're going to assume that this sequence converges to 0. So the AKs not only decrease, but the limit of the AKs as k goes to infinity is 0. If we have a series like that, then the so-called alternating series A1 minus A2 plus A3 minus A4, etc., converges. This is the alternating series test. So let's look at an example. Let's look at the infinite series 1 over square root of 1 minus 1 over square root of 2 plus 1 over square root of 3, etc. We're going to show that it is convergent, but not absolutely convergent. So we first take a look at the series of absolute values, as we did before. And if we take the absolute values of the terms, we come up with this series, just sums of reciprocals of square roots, which looks like this, or summation 1 over k to the 1/2. And of course, this is a p series with p equal 1/2 less than 1. So we know that this series diverges, and hence therefore the given series is not absolutely convergent. So if we put absolute value signs around the terms of this series, we get a divergent series. So this series we're looking at is not absolutely convergent. Now, if we go back to the original series up here again, and we take a look at the terms, they are 1 over root 1, 1 over root 2, 1 over root 3, etc., with plus and minus signs in front. And we can see that those terms are decreasing, and the limit as k goes to infinity of those terms, 1 over root k, is 0. So therefore, by the alternating series test, this series converges. So in this example, 1 over root 1 minus 1 over root 2 plus 1 over root 3, etc. This is an example of infinite series that converges but does not converge absolutely. And we have a phrase for that. Such a series is called conditionally convergent. One thing to keep in mind is this, though. If an infinite series is not absolutely convergent, and if the alternating series test does not apply, we can generally say nothing about the convergence or divergence of the original series. Particularly, the alternating series test can only be used to conclude that an infinite series converges. It cannot be used to conclude that a series diverges. So keep that in mind. This is a good test for convergence, but you cannot use it to conclude that a series diverges. Now, our last example, previous example, we looked at this alternating series, reciprocals of square roots of the integers. We saw that this series converged. Now, we're going to take a look at how we can approximate the sum of the series by using a partial sum. So our quest is this: we want to find a partial sum of this series. So S sub n, sum k from 1 to n of minus 1 to the k minus 1 over square root of k. We'd like to find it so that this partial sum is within 1/100th of the actual sum of the series. So we can write that as follows. Here is the sum of the series. We'll call it S. Here's the partial sum Sn. We want that difference, which if you write out the expansion of the two ideas looks like this. We'd like this difference to be less than 0.01. Now we're going to apply a companion result that goes along with the alternating series test, and that's this. So if we have a series that converges by the alternating series test, which we do in this case, then we have the following result. That if I take a look at the sum of the series minus a partial sum, so here is the S minus Sn from before, that difference will be less than a sub n plus 1. In other words, this is the first term not used in the partial sum. So the difference between, again, the sum of the series and a partial sum is less than the value of that first term not used in the partial sum. So the partial sum goes out to n, so the last term we use here is the a sub n term. The first not used term is an plus 1. So let's go back to our example. In our case, we have ak equals 1 over k. So if I look at the sum of the series minus the partial sum, and again, here's what the sum of the series looks like, here's the partial sum, that difference will be less than the first unused term, a sub n plus 1. And if ak is 1 over root k, then a sub n plus 1 is 1 over root n plus 1. And remember, we want to make this difference less than 1/100th. And so we see here, this is what we want to happen. So if we can make this happen, then we'll know that this term, this difference, is also less than 1/100th. Now this last inequality is a very easy one to solve. So we can guarantee s minus the partial sum Sn as the value is less than 1/100th by taking n, capital N, so that 1 over root n plus 1 is less than 1/100th. And we can solve that inequality like this, cross multiply, square, and the n equals to 9,999 is one option. So our conclusion is this. It says if we take n equal to 9,999, that is, take the sums of the first 9,999 terms of the series, that the result is an estimate or a sum that is within 1/100th of the true sum of the series. So this series converges. We don't know what its sum is, but we now know that if we go out, let's say, to the 10,000th term, so it's just a little bit further than this one, then the absolute value of the difference of these two numbers is less than 1/100th. And you can use a calculator or computer to quickly sum that series. Turns out to be about 0.599899. So the sum of this series is evidently a little bit less than 0.6, although as far as I know, nobody knows exactly what the sum of that series is. So takeaways from this video, as usual with this subject, a lot of notation and definition. So we've been working with mixed term series, that is, terms with both positive and negative terms. And we had several results and definitions. First of all, if we put in absolute values of the terms, replace summation bk by summation absolute value bk, if that series converges, then the series without absolute values also converges, and in that case we say the original series is absolutely convergent. Sometimes we'll find that this series of absolute values diverges, but this series converges. And if that is the case, we say that the summation of the bk's is conditionally convergent. And then finally, if summation bk diverges and we have no other information, then we can't say anything about the behavior of the summation bk series without doing some more work. For us, that other work will often be the alternating series test. Remember, an alternating series has a very special form. The terms alternate in sign, a1 minus a2 plus a3 minus a4, where these ak's are all non-negative. Now, if those ak's are also decreasing and the limit of the terms, the ak's, goes to 0, then the alternating series converges. Now again, be careful, don't misuse this test. If the sequence of terms a1, a2, a3, etc. is not decreasing, then the alternating series test does not apply, and we cannot say anything about the convergence or divergence of the alternating series. But again, as we noted at the beginning, keep in mind we saw the nth term test earlier in our discussion of series. Regardless of what the series looks like, if the limit of the ak is not 0, then the summation of the series, even the alternating series, this will diverge. So the nth term test is always in effect, but again, be very careful how you use these results. Finally, we had a very nice approximation result. So again, let's suppose we have an alternating series that converges by the alternating series test. In other words, it has to pass this test, terms that are decreasing in positive, then with plus and minus signs in front, and the terms going to 0. If that's the case, we can estimate the sum of the series, see how close it is to a partial sum. The difference between the sum of the series and a partial sum S sub n is no bigger than the first unused term, the an plus 1. So please study this terminology, know the definitions, and get in a little practice with the alternating series test and the error estimation result. So have fun, and we'll see you in the next video. Bye.